The standard model of cosmology perfectly maps the expansion of the universe. But when we look at individual galaxies, the math breaks down. The visible matter in a spiral galaxy lacks the gravitational pull required to keep its outer edges spinning at the speeds we actually observe. To fix this discrepancy, the standard model injects an invisible structure called a Navarro-Frank-White, or NWF, dark matter halo. It surrounds the visible galaxy with enough unseen mass to justify the high rotational speeds. But the NWF profile does not naturally predict these speeds. Instead, physicists must manually adjust the mass and concentration parameters of the dark matter halo for every single galaxy, tweaking the variables until the math matches the telescope data. This process raises a serious methodological problem. A robust physical theory should predict phenomena before they are measured. Standard cosmology is caught adjusting invisible parameters to fit data it already has. Dark matter operates as a tunable mathematical patch, engineered to align a failing gravitational model with the physical evidence. In 2026, physicist Satish Thorway published a rigorous alternative framework, Dynamic Vacuum Field Theory, or DVFT. It proposes that space-time curvature and gravitational phenomena emerge directly from the gradients of a single complex scalar vacuum field that permeates the universe. This field, denoted as phi, has two primary properties. The first is its amplitude, ρ, which establishes inertial density and stiffness. The second is its phase, theta, which governs quantum coherence and timing. Under this framework, the orbital mechanics of a galaxy are dictated entirely by the gradients and stress-energy variations within this single underlying vacuum medium. To verify this, we must put the two models through a rigorous mathematical stress test. We will compare the phenomenological tuning of the standard model directly against the first principles mathematical derivations of dynamic vacuum field theory. If the inherent properties of the vacuum field can naturally reproduce galactic observations without manual adjustments, the search for a dark matter particle has been the pursuit of a mathematical phantom. This is the DVFT vacuum Lagrangian density equation. The f of x term is a nonlinear kinetic invariant controlling the field's behavior. Varying the action with respect to the phase derives a modified Poisson equation, dictating how baryonic matter interacts with the vacuum. We apply this to the deep field limit, the low acceleration regime at a galaxy's outer edges where Newtonian gravity fails. Integrating spherically outward natively locks in a specific relationship between forces, producing the deep field force law. This exact mathematical outcome produces the baryonic Tully-Fisher relation. It strictly links a galaxy's total visible baryonic mass directly to its flat, high-speed rotational velocity. DVFT proves mathematically that flat rotation curves are a mandatory consequence of the vacuum's nonlinearity, requiring no new particles. With the math established, we can test these equations against 2025 and 2026 observational data from our neighboring galaxies, starting with Andromeda. This table shows observed edge speeds of 4 galaxies. To replicate them, standard cosmology requires manually tuning a unique dark matter halo for each. DVFT calculates these exact velocities using solely visible baryonic mass and a fixed vacuum response scale, requiring no adjustable sliders. A theory predicting data with zero variable tuning demonstrates physical validity that bespoke adjustments cannot match. The true test of a gravitational theory extends beyond the movement of stars. We must also examine the bending of light itself through gravitational lensing. The standard model assumes that the mass governing orbital dynamics is the same mass bending light. This identical mapping creates a gravitational slip parameter of exactly 1. In DVFT, light propagates through the vacuum medium. Because the medium has a specific linear response, the bending angle differs slightly from the dynamical mass. This forces the gravitational slip parameter, gamma, to naturally deviate from 1. When we examine the SLACS J0037-0942 lensing system, the measured slip parameter is 0.96. The standard model fails to predict this discrepancy, whereas DVFT predicts exactly 0.96. The path of light is dictated by the vacuum medium itself, exposing a significant gap in the standard model's dark matter assumptions. For decades, physicists have pointed to the bullet cluster, the aftermath of 2 colliding galaxy clusters, as evidence of particulate dark matter, owing to a spatial anomaly. The data reveals a clear anomaly. The gravitational lensing mass is physically separated from the colliding baryonic gas, where the vast majority of the visible matter is concentrated. The Standard Model explains this by asserting that two giant, collisionless dark matter halos passed right through the gas collision without interacting, carrying the source of the gravity away with them. This equation shows the DVFT calculation, combining normal baryonic mass with vacuum phase sector stress energy. While the gas slows and shocks upon impact, the collisionless vacuum phase structure moves past the gas, producing the exact lensing offset observed. The bullet cluster offset demonstrates the independent propagation of vacuum stress energy during a high-speed collision, requiring no dark matter particles. A comprehensive theory of gravity must accurately model the dynamic life cycles of interacting systems, like the antennae galaxies. Under the Standard Model, there are no mathematically defined speed limits for galaxy formation. To explain why rapidly spinning galaxies do not tear themselves apart, the theory relies on tuned feedback mechanisms. DVFT establishes strict maximum velocity bounds derived directly from the vacuum field's gradient energy limits. The structure of the vacuum itself dictates a physical speed limit. Energy conservation within the vacuum field allows us to calculate the exact timing of the Milky Way and Andromeda collision, placing it between 7.6 and 8.0 billion years ago. These galactic life cycles, from stable rotation to final collision, emerge as a single, consistent output of the vacuum field equations. Across every tested observable, the Standard Model requires invisible matter and constant manual tuning to match the data. DVFT achieves equal or greater predictive accuracy with fewer assumptions, deriving all galactic phenomena from the properties of one single scalar field. Future high-precision measurements of the gravitational slip parameter will soon serve as the definitive test between these two frameworks. The dark matter problem resolves when we incorporate the physical dynamics of the vacuum into our gravitational equations.